Hi everyone, in this video I'll explain how to do a finite element analysis of a 1D bar using MATLAB. This is a very simple FEA exercise that we'll do using MATLAB. Okay, so this is the basic problem, and this thing in the white is this is the 1D bar, which is fixed at one end and load is applied at the other end. We could have different boundary conditions as well, such that it is fixed at both the ends, and force could be applied anywhere inside the domain, which is between these two ends, or it could be uniformly varying load or any kind of varying load. So this is the basic problem. N is the length of your bar, F is the load applied, and the element stiffness matrix for a bar element is defined something like this. This is obtained from the variational principle by minimizing the potential energy of the bar. So you could refer to a basic FEA book to if you don't know this thing, you can refer to a book. It's not that hard. Okay, so once we have the element stiffness matrix, it is defined as like this. There A is the cross-sectional area of the element, E is the Young's modulus, L is the length of the element. Okay, so what is an element? An element is a subdomain, okay, of your main domain. Here your original domain was of length L, which is from here to here, but you have subdivided your domain into various subdomains. Here we have divided our domain into 3 subdomains. So the 1, 2, 3 are our elements, okay, and the elements are defined with the help of the nodes. Okay, so each element has got 2 nodes. In 2D or in 3D, a particular element could have various number of nodes. For example, a triangular element has 3 nodes. So likewise, various kind of elements are defined, but in simple 1D case we have element with just 2 nodes. Okay, so we have 4 nodes and 3 elements, and this element stiffness matrix is defined for each element. Here we have considered that area of the element remains constant, but you could very well use varying area of cross section for an element, but the stiffness matrix would slightly vary, and A would be inside that, and you need to perform various integrations and all, but here we'll consider it to be a constant. Okay, so let us see what is a global stiffness matrix. You know what is a element stiffness matrix. Now let us move to a global stiffness matrix. So a global stiffness matrix actually represents the whole geometry. Here the element stiffness matrix represented a single element, but the global element stiffness matrix is actually defined for the whole domain. Okay, so this was our element stiffness matrix. K is the stiffness matrix, so its size is 2 by 2. Okay, 2 cross 2, 2 rows, 2 columns, and the global K is always degree of common DF. Here DF is a degree of freedoms. Okay, so in our case, with each node there is only one degree of freedom associated, that is deflection in x direction. If rightwards is x axis, then with each node we have just 1 degree of freedom. But in 2D, for like in beams, each node has 2 degree of freedom, that is it can move in x and y also. So degree of freedom would be number of nodes into 2, but here we have just number of nodes is equal to the number of total degrees of freedom. So our DOF for this geometry is 4 by 4. Okay. Here I have taken 5 also for the general case. Okay, so how do we generate a global K? Okay, so you calculate the element stiffness matrix for an element, and you find out the node numbers associated with that element. Okay, for element 1 we can see here, for element 1 we have node 1 and 2. Okay, node 1 and 2. So we go here and we find the node 1 and 2, 1 and 2, and we put our element stiffness matrix in this block. Okay, so let AE by L be A, then we put, so this will be A minus A minus A. We put this thing here. Okay, now the contribution of the next element. So this was element 1's contribution, this is element 2's contribution. So for element 2, 2 and 3 are the pertinent nodes for this element. So we define it like this, and we put at the node number 2 3 and 2 3, at column 2 3 and row 3 we put our elements difference matrix. Let AE by L for the element to be B. Okay, then it would be B minus B minus B. So similar for the element 1 case, so we put it here. But and we add the contribution of element B, the contribution of element 2 into the contribution of element A, and we get something like this, global K. Okay, so A plus B minus B minus B. Yeah, this the contribution of element B is also added into the global K. Similarly, we go on adding different contributions. Okay, so this is how we generate a global stiffness matrix. So the next thing would be to apply boundary conditions and to partition the matrix and then solve finally the system operations. Okay, partitioning is simply discarding those rows and columns corresponding to which the degrees of freedom are fixed or specified. We'll take a simple case here where degrees of freedom are specified, and which is 0 actually. The degree of freedom is fixed. Okay, we have not specified a particular value, like displacement at this end should be something non-zero value, but we could have that also, but we'll discuss that thing later. But in this video we'll only see the case in which the displacement is 0. Okay, so this is how you do that. So let's move to the code. So here is the basic code for this basic MATLAB code. So we initialize our code by using simply length is 1, area is cross-section of area cross-section is 1, and the chunks model is 100. Number of elements we have taken 3 here. The number of nodal points would be number of elements plus 1, because you can see that because see we have 3 elements and we have 4 nodes. For this case only, it won't be actually the case for in different other geometries or other 2D or 3D problems. So K is always NNP, NNP. Actually it's DF, DF, but NNP is equal to DF as we explained earlier. And F is the load vector, which is always DF, 1, which is NNP, 1. And length of each element, which is LEL, I define it as LEL, is total length L, which is 1 divided by number of elements. So 1 by 3 is the length of each element. Now let us generate the global stiffness matrix. The range I, I plus 1 is the pertinent nodes. Like for element 1 it's 1 2, for 2 it's 2 3, for 3 it's 3 4. That's why I have taken I and I plus 1 for a particular element. And we likewise that we did it here. We put your element stiffness matrix in these blocks and add those. So this is sequentially we do it one by one. For element 1 we initially it's zeros, all zeros, so we add all the zeros with this thing at the location defined by the range, and subsequently we do it for other elements and add their contribution to the global, and finally we get a global stiffness matrix. Okay, so now we define the boundary conditions, which is fixed node is the first node, and the free nodes, this is set exclusive or is actually gives you everything but not 1. Okay, so 1 to an NP and the fixed node. Okay, so this is an exclusive OR. This is the thing. So let's you get using set exclusive OR. So from 1 to an NP it will give you everything but not 1. Okay, so this is how we get free nodes. And the force nodes is where you apply the node, which is load. So we are applying load as a free end. Okay, at the NNP node, which is the node number say 4 here. Okay, 1 is fixed, 4 we have applied the load. So and the force value we have specified 1000, and with these values we have put this 1000 value, this 1000 newtons at the force nodes. Okay, at the last node we put the load value. Now we need to partition K and F matrix. Okay, so just it's simply discarding the fixed node. So we only take the free, and for the force and the force vector, for the force vector also we take the free degrees or free nodes numbers. So finally we need to solve the system using backslash so u is k by f, okay, partition u, and the global u would be I've defined a global u so that fixed things can be also be put up in the same vector. So u is zeros, u free nodes is up, rest of all is 0. And for the visualizing I'll explain later. So let's run the program and see one by one what are we getting. Let me change this to this so that we could see what is happening. Okay. So this is for the first element. For the second element we get this. Okay. In this block we have added. For the third element we get this. So this is how we get the global stiffness matrix. So the fixed node is 1, 3 nodes are 2, 3, 4, force nodes is the fourth node, force values. So let's see what f looks like. F looks like this at node number 1, 2, 3, 4. Only at node 4 we have applied 1000 meters. Okay, so now the partitioned KP and FP looks something like this. So we have partitioned, we have discarded these two loops, and we have only used this much. So from here to here we have used, which is this. And for the load vector also we have discarded the first element. So we get this because that particular DF is fixed. Okay. So after solving, we get the UP is this and U is this. Sorry, U is not yet evaluated. So we get this is our final solution. This is simple visualization that I've done. Okay, so let's show you final results. Still waiting. This is how we get the result. This is the contours. Displacement at the free end is 1 and it's 0. Okay, so how did we generate this visualization? As we defined the x coordinates at every node, y coordinate at every node, okay, and this x diff is the deflections at every node, y df is which is always 0. So this is how we calculate x coordinates. This is a simple loop by adding LEL to previous x. Okay, so this deflection at every node, and we set the last to an end a very large number so that it terminates at the end, not a loop, and we patch it, only patch, curve patch. So this is we have the C data. So this is the color for the contouring. We have specified the C vector to the displacement so that the vector you get on the color bar shows you the displacement values. So this is how you patch it. Okay, enter productivity, shading for inter and line width. So simple. Okay, so color map is checked, so it goes from blue to red, and this is a simple command to get minimum maximum values, to show the maximum values, and this is how you get it. Okay, now the next better visualization technique is to use this code. This is better improved code that actually generated 2D polygon patch, contours 2D polygon patch. Let's see the results for this. Got the result. Yeah, so there's the result. we had 3 elements. See, this looks better as compared to that one, and you can see the code. So here we have used the 4 coordinates for each patch, generated 4 coordinates, and using normal patch we have used for the color interpolation. We have used displacement set the particular nodes. So let's try once more using more elements. That is, let's use 25 elements now. Let's see the final result. So this is what you get. Problem, here are the displacements, x and y coordinates, and simply you can get the stress and all. Also we will discuss in that thing the post-processing. It is generating stresses and internal forces and all, the reaction forces, and definitely the contour plots similar to this thing for our bar. Okay, so that's it for the video.